Yeah, okay. So yeah, hi everyone. Welcome to another session of the Bangalore Theory Seminar. Today we it's no, uh, okay, yeah. So hi everyone. Welcome to another session of the Bangalore Theory Seminar. Today we have Professor Suryajith Chillara as today's speaker, and so Suryajith is an assistant professor at the International Institute of Information Technology, Hyderabad. Prior to this, he was a postdoc at University of Haifa and at IIT Bombay. He did his PhD from Chennai Mathematical Institute under the supervision of Partho Mukhopadhyay. His research interests lie broadly at the interface of algorithms, complexity theory, and coding theory. So, over to you.
So now this talk is about another dimension, information theory. Yeah. So today I'm going to talk about this fractional subadditivity of submodular functions, equality conditions, and okay, that's a mouthful. Okay, so I'm primarily an algebraic complexity theorist, and I also dabble in algorithms. But this happened. So if Jay Kumar was here, right, Jay Kumar would know most of the talk anyways because we're standing on the shoulders of Jay Kumar with respect to this information theoretic proofs. So and I could have also used him as an oracle. In case I'm stuck, I can just like say, Jay Kumar, please. Okay, so there is this really nice note of entropy and counting that Jay Kumar has. So Gautam was teaching that at IIIT, and Gunank was a student in that course. And then we started exploring, like, so, okay, so this is all nice. So what does this imply? So entropy tools for counting, entropy tools for, so let's see like one of the applications, entropy tools for doing proofs otherwise, which were not easy without entropy, right? So these are like, that's a beautiful note. And then we started thinking about one problem there, right? And that problem generalized to what is called fractional subadditive submodular functions. So let's start at a basic note where we started thinking about this problem. Right? The first place that we started thinking about is entropy and Shearer's lemma. So Shearer's lemma is defined in terms of entropy. Right? So here I'm just going to put some basic definitions of entropy. So for example, like entropy is like if you talk about uh, so what do you call entropy? Entropy is generally defined as the uncertainty in the system, right? So the other way to think about it is, so I can think of it as px. So where is that? Sorry. Uh, so px. So this minus sign I can say px log 1 by px, right? So this 1 by p is like log 1 by p is the amount of information needed to like rather than amount of information you realize when such an event happens, right? So that's the log 1 by p signifies, and this is a weighted average over that, all the outcomes of the process. And then similarly, we can define what is called a conditional entropy. Right. So if you have a random variable, you can actually define like conditional conditional equivalents of this entropy. So x is a random variable. And similarly, you can have x conditioned on y. And then you can naturally open it up using your probability definitions as to saying that, oh, I'm going to open it up with respect to every what do you call invocation of y. And so probability py times the entropy of x conditioned on the y taking the value small y. Right? And then I can open it up further, and then I'm going to get this. Right? And the other important point is conditioning reduces entropy. Okay, so if you have an uncertainty with respect to variable x, so having some side information is going to reduce the uncertainty. Right? So that's the take about conditioning reduces entropy. And this equality happens if and only if x and y are independent random variables. Right? If y is not giving me any information about x, then the uncertainty remains the uncertainty as it were before. So this is entropy, and then it has some really neat properties. So these neat properties are something like I can think of it as I can expand this as a chain rule. So one simple example that I've written here is if I have two. So think of it as when I say x comma y, it's a joint distribution of x and y random variables. And when I'm only using x, it's like the marginal of this joint distribution. right? It's going to be h of x. So this is a property that you can write. H of x comma y is h of x plus h of y given x. So that's the chain rule. And like instead of two variables, I can actually make it into multiple variables, n variables, for example. So if I have x1, x2, x3, I'm just going to write as x like x1 plus and so on. And like so here it says. So the way I have written it is this is nice combinatorial structure saying I have x1 and condition on all variables until I minus 1. Right here, that expands to h of x1, x2, x3 would be h of x1 plus h of x2 given x1 plus h of x3 given x1, x2. So this is nice properties that you can verify by writing in terms of the probability terms. And the important point is the entropy. There is a subadditivity given for entropy. So just stare at this term above. If you stare at this term, each of these conditional expectations is at most h of xi. Right? As I said, conditioning reduces entropy. So that means if I can replace each of these terms with h of xi, and I know that this is true. So this is a subadditive structure. And this equality holds if and only if each of this, so this is an equality. And when I actually need this to be equal to this, then xi has to be independent of all of those before it. Right? So that's and these are the simple facts we'll keep using again and again. So the entire set of entropy and counting principles of Jacomar's notes mostly rely on these basic what do you call inequalities. And then, so you talk about when is this maximized? For what distributions is it maximized? So when do you have? So if you think about it intuitively, it's like if you have a distribution which is uniform, so anything can occur. If I have some cognitive x many outcomes possible, when each of them is equally likely, then I have maximum uncertainty, right? So intuitively, that tells me that the uncertainty is maximized for uniform distribution. You can prove it mathematically, but again, intuitively also, one thing good about entropy is there's a lot of intuition that also runs along with the math. So that makes our life much more simple. So, right, and yeah, so these are what are called Shannon type inequalities. So, I mean, whatever entropy definitions that we have used, they're defined by Shannon, and then these are just working things out with respect to the math specified by the fundamental thing where I have defined h of x as summation over all the outcomes p of x. So p of x times log of 1 by p of x word. Right. So that's the basic definition, and these are all the properties that inequalities that I have. And so whatever we have discussed in these two slides, these inequalities, these are called Shannon inequalities, Shannon type inequalities. So I'll come to that fact later, why we only talk about Shannon type inequalities in this paper and not something else. So along with that, we define what is called a mutual information. Right? So mutual information is like, suppose I have this random variable x and random variable y. I want to understand what is the mutual information between them. Right? So what is it? So if I actually stare at this, so I have h of x minus h of x given y. Right? So now what is the information? So h of x. So let's take this instance. So when y is independent of x, so this is going to be h of x minus h of x. That is 0. Right? If they are independent, so the value is 0. If they're dependent, if y and x are so let's say y completely describes x, in which case there is no uncertainty here. This is 0, and this is h of x itself, right? So that means this is actually measuring the amount of dependence between these two variables, right? It's highest when they're dependent, lowest when they are independent. It's like kind of similarly. I mean, and this is kind of symmetric in the sense that there is no ordering here with respect to the semicolon there. There are two entities, and I'm looking at the information that they share. So that's a mutual information there. And then if you work things out, you'll also get, so it's just basic brute force expansion of these formulas. And you can also have a chain rule here. Right? You can actually write as x. So here I have x from. So just to make this notation a bit more explicit, I have random variable x here. Here it is a joint distribution on y and z. So here I only had two random variables, and I had distributions on these random variables. Now I can also talk about this mutual information between a distribution which is only on x and joint distribution on y and z. Right. So this is the setup that we have. So let's work out some simple stuff, right? So let's take this inequality that we'll call this Shearer's lemma in its most basic form. Right? If you look at this, so initially, if we were to write it as a subadditive, I would have just said h of x comma h of x comma y comma z is going to be at most h of x plus h of y plus h of z. So that was my subadditive form. Now let's look at a slightly stronger inequality, which is of the form 2 times h of x y z is at most h of x y, h of x z, and h of y z. Right? So think of it as you have a full set x y z or 1, 2, 3, and then these are my subsets 1, 2, so 1, 2, 2, 1, 3, and then 2, 3. Right? That's we'll just like slowly translate into that way of thinking about these random variables. But let's prove this inequality. Very basic inequality. So I have the first term here on the RHS, and the first term I'm just going to use the chain rule and then open it up. And again, the second term and the third term they're using the same things, right? So now I use a fact that the conditioning. So conditioning reduces entropy. So I use this, and I can use the same thing here, and use the same thing here, right? And now, so I have 2 times h of x, I have 2 times h y given x, and I have 2 times h z given x y and z, right? So I write this up, and then as it turns out, this is actually equal to x y z, right? So most of the proofs in entropy, Shannon type proofs, or for Shannon types inequalities, they are linear combinations of the basic fundamental inequalities that we have seen in the first 2 slides. And as it turns out, for all, I mean, if you have 3 random variables, Shannon type inequalities characterize all possible inequalities possible over the three random variables. So this is a like a very, very celebrated result. But if you go to 4 variables, it is not true. So there are inequalities holding over 4 random variables which cannot be represented using linear combinations of the aforesaid Shannon inequalities, Shannon type inequalities. Right. So the Raymond Young and Zhang have this paper which is like celebrated, saying that, oh, there is an information theoretic inequality on 4 variables, which does not follow from the linear combinations of all like the basic inequalities which we have seen. So yeah, so this is, as it turns out, this inequality actually uses the simple principles of conditioning. Right? Conditioning reduces it. So I said equality conditions in my title, right? So I have an inequality, and let me wonder about what is the equality condition in this. So I claim that the equality conditions would actually be this. Okay, so let's look at a simpler one, which is this. So rather this. So what is this? If I actually look at this, if I stare at it, and if I look at the formula there, what I get is if this inequality has to become equality, each of these inequalities should become equal, right? So now I investigate the situation where each of them becomes an equality, right? So if I stare at this, if this is if the h of y is equal to h of y given x, that means x and y are independent of each other, right? And then if I stare at this, I know that z is independent of x and y. I mean, so z is independent of x conditioned on y, right? And then if I stare at this, z is independent of y conditioned on x, right? And if I put these 3 together, if I take a linear combination of these 3 together, I get these 2. So I can also work this out like if it. So if I write I of x comma y z, so let me use this. So I'm going to write this h of y z minus h of it. So then I can write this as h of y plus h of say given by this is h of yes, I need to be careful with respect to what argument I take. We have x plus so minus h of so I have this there and I have this here, right? So this is one set and these are the other set. And they become zero, right? So now the first thing that I get is this is zero. And again, I can show something similar for here as this as well. So y and z are independent. Sorry. So y and z are independent given x, right? So now if I simplify this, just brute force using the basic chain rules, what I get is x is independent of y comma z and y and z are independent, right? So that means all x, y, and z are independent. So the statement that I can make here is that this inequality becomes an equality if and only if x, y, z are independent. So I mean, so the other side, I only proved the one side. The other side is trivial in the sense that if I can just open up in terms of h of x and z, h of x, z. So if x, y, z are independent, then the equality showing that it is an equality is not a difficult task, right? It's just open it up in terms of chain rule, and then like you don't have the conditional terms. So this is the basic form of Shearer's. So here, what you can observe is that this set and these subsets of the set on the left, they're very nicely structured, right? They're a family. You can think of them as you have n size family. I mean, so you have a family of n elements, and rather you have n elements. And on the right side, this is a family of subsets of size exactly equal to 2. All subsets of 1 to n of size equal to 2. Right? So this is a structure. So you can think of this as all the elements available, and these are entropies over the subsets that I have. Right? So that's one way to generalize what I have as Shearer's. So it need not be so structured. Right? So let's see, like so one example, since I've been talking about this entropy and counting method. So one favorite example that I have, and it's also Jigma presents it in every talk. So this is the celebrated Loomis-Whitney inequality, right? So Loomis-Whitney inequality says, suppose I'm looking at a 3-dimensional space. So this can be spoken about d dimensions as well, but I'm just talking about the 3-dimensional space. And in 3-dimensional space, so you have there are some points in the space, right? And I have 3 different planes, right? Like x, y, y, z, and zx planes. So I take the projections of these points onto these planes. If I take these projections, they're going to cast some shadows on it, right? So now I want to count the number of shadows on each of these planes, and I want to get, based on these shadows, I want to get an estimate of how many points you have in overall, right? So this is like, suppose I have n points and I have 3 projections, n1, n2, n3. So I want to get an estimate of n with respect to n1, n2, n3, right? And the Loomis-Whitney inequality says n square is at most n1, n2, n3, right? So, well, so this is it's a combinatorial result. Obviously, people would have used like heavy combinatorial machinery to prove. But you have a very simple proof for this using entropy. So suppose you have n points, right? No, you assign a distribution onto these n points such that this distribution picks each point uniformly at random, right? So that means the joint distribution of this xyz, the sorry, the joint distribution of this xyz, so it's uniform over the set of points, right? So now, so I know that if I look at its entropy, it's maximized because it's a uniform distribution, right? So, but I don't know what to do here because I don't have it. So I know the distribution of the points S, but I don't know the distribution of its projections. It's okay, but I don't know. I don't have to really know the distribution. I can just simply bound it by whatever it is. It is bounded by when it is a value when it is uniform, right? I can just take it as so h of xy is bounded by log n1, h of xz is log n2, and yz is log n3. So now if I actually take anti-log, what I get here is that n square is at most n1 into n3. Right? What was a really long proof, and this actually scales up to multiple dimensions as well. So it's no longer called Loomis-Whitney inequality. I forgot what the inequality is called in higher dimensions. So you can also have that. So you can actually say if I have a d-dimensional space and I have points in this d-dimensional space, I can actually look at the projections onto d-1 dimensional spaces and apply this inequality. I mean, you'd have n to the d-1 is at most the product of the cardinality of the projections. So we'll come to that. Actually, so here we are not using that at all. So I mean, okay, so it's orthogonal is implicit in this because I'm actually saying that so this xyz is a marginal of this random distribution restricted to only xy, and so it's not explicit, but it's implicit in the way it is defined. So yeah. So now if I have, so in this example, as it turns out, I have 7 points and I have 5 free and 5 projections. Then what you get is 49 is at most 75. Right? So again, so if we want to do a equality, when does the equality hold? Right? So the equality holds when the structure is exactly a box. Right? So it's like, so you have this box, and that's when the equality holds. And the equality conditions for this Loomis-Whitney have not been studied in literature, and this actually has an implication I'll talk about soon. Right? So, right. So here we're using this. The summary of what we've done is n square is n1 into n3, and then the equality holds if and only if x, y, and z are independent. And the support of that means the support of p, x, y, z is product of supports. So you can think of it as this distribution that you have is a product distribution. So generalizing this is saying that I have a product distribution. So this p, x, y, z is a product distribution. Right? And this set of points is actually a Cartesian product. So now let's just gear it up a bit. So if you gear it up a bit, let's look at this family of subsets. So as I said, initially we have considered very structured family where I have all the n elements, and then on the right side I have subsets which are very structured in some 2 out of 3. It's rather all 2 out of 3. So here let's make it a bit more general. So I have a family F of subsets of 1 to n such that the number of repetitions of each element is at least k. Right? And if this is the case, so if this is the setup, then for any set of random variables x1 to xn, having this structure, you have k times h of 1 to n is at most the summation of entropies of this restricted to this subsets in this family. So one thing I'll also say that this subsets can be repeated. I'm not calling it a set of subsets, I'm calling it a family of subsets where I have no restriction that this subsets need not be repeated. Right, the other way to think about this is these subsets are vertices of your hypergraph. If this were equal to k, then I would be looking at a k-regular hypergraph. Right, so I have some n elements. I'm looking at subsets of these n elements, and in a hypergraph, like two vertices have an edge between them if there is an intersection. Right, so now this is a kind of so this is a hypergraph way of representing the family that we. But this is like 2 out of 4. Yeah, this is 2 out of 4 family. So this is the general form of Shearer's inequality. I mean Shearer's lemma. And this actually generalizes a lot of inequalities that were known before. Right. So there is a Hans inequality which says where this family is of a very specific kind, one complement. So this is exactly for the basic Shearer's lemma is Hans inequality. And you can also have a generalized Hans inequality where you actually say, I'm looking at subsets of size t each. So now let's get to what is called. So here, if I actually take this 1k to the other side, I have the following thing happening here. So let's say this is equal to k, right? So I can write this as, can I use this? I have h of x1 to n is equal to summation over this family f belongs to this scalar 1 by k times h of xf. So this property that I have is that for all elements I in n, summation of 1 by k for uh, for all f such that I f belong to the cal f, I belong to f, so this is equal to 1. If I have an equality there. If I don't have an equality there, this greater than equal to. So what does the first condition say? It says that the number of subsets in which an element I appears is at least k.
Yeah.
Right. So now if I actually move the 1 by k to the other side, if I actually sum of the coefficients of this subsets in which I is there, so that will at least be 1. Right. So I'm essentially saying the count. So I'm just replacing this as this one where f is cal f, I belongs to f, is at least k. I've just written it in a different form. So that's what I have done.
Like there's no in the cardinalities of the sets in the family can be okay.
It can be arbitrary. I only care about the repetition.
Right? So like singletons is a trivial thing.
Yeah, singletons is a trivial thing.
Yeah.
So singletons gives you that what do you call the chain rule with by using that condition, like if you let go of the conditioning to the subadditivity.
Yeah.
Right. Yeah. So now, all it says is I can treat them as coefficients, some coefficients. So here my coefficient is a very specific form which is 1 by k. Right. I can generalize this to some arbitrary coefficients gamma f such that I'll make it into 2 different kinds. So one kind here I disambiguated saying that the number of repetitions is exactly equal to k and the number of repetitions greater than equal to k. Right. So in a setting, I have the number of representations exactly equal to k. I'm just going to call it a fractional partition. And when I have the number of representations at least k, I'm going to call it a fractional covering. Right?
The redimension of this XOS fractionally subadditive.
Okay, so the thing is, these have been studied in multiple literatures and they have not been looked at in a single lens. So for us, the way one place which unifies a lot of this literature is the work of Madhiman and Titali. So like this, this is a work which actually puts together. So for example, this fractional subadditivity appeared in Feige's work of this XOS functions.
Yeah.
So this valuation functions, he actually brings in fractional subadditivity. And then there is a place where in statistical physics, so people have been talking about this fractional subadditivity in different names. So there are multiple papers, and then even Madhiman Titali's work, they say that they didn't know about this statistical physics reference until this person called Alan Sokal, he actually pointed it out in a conference or workshop that this thing had been there since 70s. So
Context. Yeah, studied it. Maybe. Yeah.
So
late 70s. Yeah.
So this has been studied over and over again in different names, but so I think Madhiman Titali actually started calling it like the fractional subadditivity. Right. So a generalized Shearer's lemma now would be something of this sort, where I have h of x1 to n is at most the summation over all the subsets in the family with this, like it's like kind of a weighted average of your subsets, the entropies of the subsets. So whatever I'm presenting, I'm actually presenting first as entropy, and then I'll say that entropy is a specific example of a submodular function. And then like whatever I'm talking about here will hold in very, very good generality. Right. So this is my, and so this Shearer's lemma has been used in combinatorics multiple times in like various results. And then it has applications in graph theory. So for example, using this, they have been using this and a slightly stronger version of this. There have been applications of counting homomorphisms and then like counting independent sets. There are a lot of counting problems which can be tackled with this formulation. So to give you a bit more of specificity, what I'm presenting here is what is called a weak form of Madhiman Titali. This is a stronger form as well. So a stronger form gives you even better results, but the equality conditions don't really like mean much in that setting. So we were interested in equality. So we wanted to look at the weak form of these. Right. So let's, I mean, if we want to prove the generalized Shearer's lemma, so the proof is very reminiscent of what we had done initially. Right. So just like, okay, suppose I have F, a subset which is 2, 4, 7. Then I'm going to write it in a way that okay, I'm going to look at h of xf. And that h of xf I can write it using chain rule. So I first order them in the ascending order of their indices with some permutation. I don't care which permutation, fix a permutation and with that work. Right, and then I'm going to write it as h of x2 plus h of x4 given x2 and so on. Is a chain rule. And then to bring it into so I use this conditioning that uses entropy thing and say, okay, if you look at the initial chain rule, the way it was written, it says h of x1 to n is summation over h of xi conditioned on all random variables until the index I minus 1. So that I need to bring in, right? So this I can bring in here. So instead of x2, I'm going to add like x1, x3 as well, and so on. And then this is nothing but h of for all I in f, I have this, right? And then so I for an individual like h of xf, I have this, and then I'd sum it up over. So I have this on the right side. So I computed this so far, and then for this. So I have this as it were, and then I'm substituting whatever we got here into this. And then I sum. So I take this and I just like do a exchange of summands, and then what I get is. So I know that this quantity by itself, summation alpha f for all f such that I belongs to f. So this quantity is at least one. Then I get. So there is one inequality here and there is one inequality here, and I get this. It's a simple proof. Right, so this again standing on shoulders of Jigmar. So now, yeah.
Characterization, like the 5K thing and like how it seems, is it these things have like a maximum interpretation as well. Like any such function is like maximizes linear functions. Is that
Yeah, so we'll talk about that here. Yeah. So okay, so one of the things that we actually consider is the family that we have. So we'll assume that the subsets, so no two elements appear together. If they appear together all the time, then I'm going to treat it as a one variable. Right? Assumption that I'm going to make, and then so the ground set is not part of the family. Then that inequality does not really make sense. So basically without all of these conditions hold without loss of generality. In the sense that if I have ground set appearing on the right side, I can just move it back and reduce what do you call the fraction accordingly. Right, and then we assume that these quantities are greater than 0. So in some literature, what they say is I have a family, and then they say, so for them, they also stated in terms that I have all possible subsets, and this is non-zero for only a few subsets. And they write it like their interpretation is that way. That we have a different interpretation saying that gamma f is strictly greater than 0. We only consider those subsets. So now what we show is. Huh?
Oh, gamma is the partition.
Yeah, gamma is the coefficient of this partition. The covering. And then there's also the other thing called packing. So that's the other end. Like I'm not going to talk about it in this talk, but like most of these results also hold there. So one thing, so if you have a family of subsets, so okay, so let me just define the gap. So this difference between RHS minus LHS, I'm just going to call it a gap. And this gap is, so gap has some useful properties that we'll actually look at in a while. So the main thing about this result is saying that if you have a fractional partition, regardless of what set family you give to me, then each of these random variables are independent. If there is an equality, then all these random variables are independent. And funnily, it has not been studied and it has some applications as well. And if you have the gap, so instead of a partition, you have a covering. Then, so for all those variables where you have this for all those I such that summation alpha f is equal to 1, those are independent. And this is the most interesting part. So wherever I have summation alpha f greater than 1, they are constants. So to give you context in terms of the, so if I look at it as a hypergraph structure, so all those elements which appear exactly k times, they are independent. And those that appear greater than k times, strictly greater than k times, those are all constants. So this is a very interesting thing that we actually found.
The requisite for the theorem is that you're given this random variables,
Yes.
and you're given
And a gamma.
And an alpha and a gamma.
Yeah.
Okay.
So given a family, given a gamma, then this holds.
In some cases, it is conceivable that this might certify independence very substantially.
That is what we are hoping for.
Okay, as a distribution testing. Or...
Yes. So that's the application that we have in mind. Okay. So for example, so I'll talk about we'll actually see that so it is not with unconditional. If you have some side information, for example, checking modularity becomes easier.
Yeah, if
the equality is giving us that extra power.
If the sets are of relatively smaller size compared to n, then you're only sort of required to test
yes
entropy, and that will certify
Yes.
over a very large set.
Yes.
Yeah.
Yes. So that's the application of equality that I'm doing. Yeah. So yeah. So basically now if you I'm not going to go through the proof of this. So this is like this is what we have seen before, and then like this proof basically reduces this problem into this problem. So slightly, so slightly non-trivial, but okay. So suppose I just to give you a proof sketch, I'm going to just say suppose I have this family. I have some elements which occur twice and some elements which occur thrice. See, one trivial thing that I can do is I can actually reduce this family to another family by ignoring these random variables. And here, what I have here is a set where each element appears exactly twice. So if you have to work as an example, so I have this, with this family, I have this equation, right? Now I know that I'm breaking this Fi, F3 and F4, I'm breaking it into a subset F3 prime and this element 1, and F4 prime and this element 2, right? So this element 1, so I'll have this simplifies to for F3, I have an additional term here. For F4, I have an additional term here, right? And I know that this is a condition where all the elements appear exactly twice. Then this problem is reduced to my original problem of where I have a partition. Whereas this one, I know this one tells me that all elements are independent. When I have all elements are independent, so I know that this one will be 0. And each of them is a strictly positive quantity, then each of them has to be 0. So here what I get is h of x1 conditional on x2, x4 is 0. That means x1 is dependent on x2, x4. And here I get that x1 is independent of x2, x4. So both of them together tell me that they are a constant. But there's a slight caveat here. So this reduction, so we assume that these elements do not occur, pair of elements do not always occur together, right? So now it may be the case that you may have a family that you may not always do it in a case that you cannot always reduce to a case where you have exactly k repetitions without encountering this place. So then you can actually, so there is a good 2-page argument for that. This is a problem if you do trivially, but you can use combinatorics, power of combinatorics to prove the result. So that is the most interesting part in this. So yeah, otherwise the proof would be trivial and why do we even need? So then okay, so one thing as I said, Loomis-Whitney looks very 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 simple. Like in retrospect, it's not simple at all, but it's in retrospect it looks like it's like a simple identity which using entropy can prove it. So what happens if the inequality, the equality almost holds? Right? So this is what is called a stability result, where, so you understand what happens when the equality holds. So now I ask you what happens if the equality almost holds. Right? For example, I said if the equality holds, what I have is a box. Right? But what happens if it is almost equal? So does it say that it's almost a box? It is true that it's almost a box, but that requires a non-trivial proof. So so this looks like sorry, what am I doing? So this is from Ellis, Fredgut, Kindler, and they actually showed that. So they showed that one of these if the inequality is almost true, then it's almost a box.
Just a box.
So what does this mean? So if I have this mutual information between this so even so I'm saying that with respect to every direction, every coordinate, I have this mutual information bounded. That means it's almost like it's yeah. Yeah, so it's like slightly some there is some width on the side. So this is the information saying that yeah. So their statement is if so the mutual information between a one marginal versus the complement marginal is small for every marginal. And this holds in any dimension that you want. right? And so if you set this epsilon to be 0, then that is the equality. But if you have epsilon non-zero and something close, then you have the stability result. So the stability result says that, so if the equality almost holds, then the conditions for which the equality holds almost hold as well. So that's a very crucial part about the stability result. And then, so what we show is you can extend this further and say that it's not only for a marginal, but it also holds for every set S that you consider in the family. Right? So so it's not only the mutual information small with respect to the margin, just those one marginals versus n-1 marginals, but also for these. Right? So I mean, I'm not saying that both of them together add a lot of value. I'm not saying that this is the superior or whatever. I'm just saying that these are complementary in nature. So as it turns out, given the time, I'm just going to go through this fast. So the thing is, we've been wondering about the application of why is fractional subadditivity so important? And what we observed was this fractional subadditivity, or the gap that I was talking about, actually captures a lot of information multivariate mutual information measures in information theory. For example, total correlation. So what does this mean? So this is the gap between the subadditivity, right? So if you put together the individual marginals, how much do they differ from the entire joint entropy, right? And then you have, so without this one marginal, so there are this multiple, so one measures redundancy, the other measures the dependency. So you have dependency between the random variables, and so on. And all of this becomes special cases of this gap that we define. So gap is not only important as combinatorially, it's also important in information theoretic measures, where this is what do you call a measure that encapsulates already known measures in a way. So this I'm not going to I have not specified condition on F complement, but this is related to, I've only shown you one side of the inequality. So there is the other side of the inequality, which I pushed into the carpet when I said. So I only said h of x1 to xn is at most some quantity, some fractional subadditive. It's also at least some quantity, where the at least quantity is given by gamma f, h of f, conditioned on xfc. So that is in the paper, but I'm just going for the presentation. I just put it on the carpet. Right. So there's the same thing. Then you can also characterize. So even if you have two sets of random variables, you can actually characterize these. Okay. So one of the important things that Madhavan Tetali first pointed is that all of these inequalities, they reprove this matrix determinantal identities in a very simpler form. Right? So this is a fractional subadditive for a fractional partition gamma and a family of subsets 1 to n. So this thing is true. The star is just pointing out this inequality, but it's not saying much more. So here, so you can define a distribution which is so such that the entropy of the distribution is some log of these. And again, yeah. So, and then you can actually show that the equality in these inequalities holds if and only if K is a diagonal matrix. And then that recovers a lot of equality conditions here as well. Right? So, yeah, so let's come to the most generalized form of what I've been talking about. So entropy is one submodular function. Right? So I define a submodular function as follows. So a function is submodular over the subsets to reals if f of the most general form that this state is f of s plus f of t is at least f of s union t plus f of s intersection t. Right? And so it's also called diminishing returns. It also exemplifies diminishing returns. For example, it may be the case that if for all S subsets of T, so f of S union B minus f of this difference, so for all S and T, so T has more elements than S, right? Adding more elements, so it's not very beneficial in some sense. So there are multiple examples. So basically, entropy that we spoke about so far is a submodular function, right? So yeah, and so when we have the inequality the other way, it is called supermodular, right? And when it is both supermodular and submodular, it's modular, right? So you have, and so one thing that is true is so what we have is the submodular functions. Our definition is defined over subsets, right? Now, if we take the valuation of our empty set to be 0, then we know that this f of s, if it is modular, I mean, if f is modular, then it can be broken as some of these linear terms, some of these individual terms. There's some linearity over here, right? And in general, for any submodular function, this is true. In the sense that if the equality holds for a submodular function, then it is modular. And if it is, so if the equality holds, then it is also linear. Right, so that's a more generic way of talking about equality and linearity being this. Right? So whatever we said for entropy, instead of entropy, we define a function. I mean, so we state that in terms of the submodular function f. Right. So I'm just so here we have this. So there is one caveat here that we want f to be non-decreasing for this to be true. And like so it's a facet of the proof than anything else. No, actually, so it's not just a facet of proof. Like for other functions, you know that this inequality is not true. You can find counterexamples. Right. So then yeah. So the same thing restated in the most general form. And as you're saying that there is there are applications in game theory, and the place where we actually picked up is Fige's notes on these XOS functions, where yeah, so this is maximally well where utility functions are, and this shows up in multiple places. And one quick example, if I can talk about, is the submodularity. So suppose like if I have a function f, right? So if it is submodular, then to test that function, I just need to look at a few places, right? And also the stability point of view is also giving you some sort of like closeness measure for property testing, right? So there are applications of this characterizations of equality also because of stability. Because almost closeness actually has a lot of value than the equality itself. And the equality gives the almost close values. Right, so here if I have this function, if it is modular, then I can actually write it as summation of the singletons. And the summation of the singletons, so it's I may have an like a massive set in which I can only query, I only need to query at this very simple points. And I would have a modularity testing. Of course, this is using the side information that the function that I'm starting with is submodular, right? Or it's close to being linear. I mean, I'll refrain from saying this, but in more generality. But here, if it is almost modular, then it's like close to being linear in some measure. Right. So again, the proofs follow the same. So Shannon types inequalities, conditioning whenever you want, and so as it turns out, all the proofs that we have seen are linear combinations of the basic inequalities we have seen in the beginning. Yeah. So again, there is a stability result stated in the more general form. If the gap is small, then this marginals, the mutual information is also small.
Curvature condition of submodular function.
Yeah. So coming from this, I don't know the. So I want to talk to you about that. Like what is? Yeah.
Like you said, near linear.
Yeah.
It's captured through like the curvature condition. Like it's very. I mean, this it's not exactly the same, but I think you can. Yeah, it's and it does. I mean, it says that if this is small, like for example, instead of 1 minus 1 over e, like this standard, you get better and better approximate. Like I mean, if it's a linear function and you run the greedy algorithm, you're optimal.
Yes.
And if it's complete, so the 1 minus 1 over e is for like where the curvature is really bad. It's the worst among submodels. So the smaller this epsilon.
Yes.
So it's a nice, I'm kind of making a guess here, but probably what you have is that if the gap is small, then you get better approximation.
Yes. I mean, we're not proven that explicitly, but so I mean, so which is why I'll refrain for me. So we hope that that is the case. So I mean, like with all of these, it may be true that it may not be true as well, but until there is a specific proof for it. Yeah. So that's the hope actually. So the performance guarantees in optimal problems is exactly what you're talking about. Like if you have an optimal problem and in that greedy strategy happens to be the optimal strategy for modular functions. And if you can test, like if you know that the function is modular by checking the equality conditions, then you can directly apply the greedy strategy rather than. So basically, we actually study fractional subadditivity for the way we study in the paper is like we actually studied for submodular functions, and entropy is a special case where like a lot of entropy, you reprove some older proofs, and yeah. So you can also do that for other submodular functions. So there is a lower gap. So I said I only spoke about the inequality h of x1 to xn at most summation alpha f h of xf, right? Then so on the other side h of x1 to xn is at least summation beta f h of xf. So beta f is a fractional packing, and with lambda on both sides, that inequality is also true. So that is what we call lower gap. And then this is also true about matroid. So for example, it explains a free matroid, for example. So then, so you also have these for relative entropy. So yeah, there's. Thank you very much. Oh, thank you. Thanks. Honored.
Nice. Like this is again coming more from the